In pursuit of sharing technical knowledge and just to gear up the new generation of engineers, myself Pranav is here to deliver today's presentation, Power Transformer Part 27. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with basic importance of composite resin silicon bushing. Composite resin silicon bushing is the obvious combination for increased reliability as a non-condenser, non-graded type dry bushing, which enables to benefit from the advantage of silicon rubber insulator by getting rid of brittle porcelain and oil explosion risks. In contrast with porcelain bushings, which are comparably delicate and fragile material, composite resin silicon bushings are constructed with tough and resistant resin and silicon materials. These bushings are much more stronger but lighter in weight, as well as much more durable and flexible. Particular type of bushings has to offer outstanding performance in all types of environments, even highly contaminated areas you can use, and has the ability to withstand severe thermal shock. Composite resin silicon bushing insulators have a greater dry arcing distance than porcelain insulators. Thermal coefficient of expansion of epoxy resin is of much less than that of porcelain, and at compression strength is 4 to 6 times higher than that of glazed porcelain. The possibility of partial discharge, that is, possibility of occurrence of partial discharge, is also comparatively low. See the diagrams, composite resin silicon bushings. Now, we start compound filled bushings. A compound having insulating properties is thus to be used as a filler material at the contact gap or passage between the main conductor insulating surface and the bushing internal surface, and it acts as a protective barrier against any ingression or entering moisture in between. The successful application of epoxy resin protective layer would have been effectively eliminated the issues related to degradation of dielectric properties of the conductor surface insulation, particularly when applied in conjunction with composite bushing housings in place of porcelain. Such type of technology for bushing construction has shown the ability to bear different weather conditions and thus to be recommended for transformers of voltages up to 33 kV. Condenser bushing, the most vital one. The bushing as selected for allowing high voltage or extra high voltage conductor to pass through the grounded walls of power transformer that must have to withstand the most consequential effect of the electrical field strength, which thereby produced within the bushing insulation. Leakage path within the bushing insulation may have to develop as corresponds to certain increase of such electrical field strength. This phenomena, whenever exceeds the dielectric strength of the insulation, then there would have been punctured the insulation and allowed the electrical energy to conduct to the nearest grounded material, causing burning and arcing. So, it is evident that between the bushing mounting flange and the conductor would have been the most highly electrically stressed area, especially at voltages 25 kV and above. It was become evident to have a better distribution of the electric field generated across a bushing. Condenser bushings are the devices in which graded capacitance that has to be incorporated by means of applying concentric capacitor foils embedded at regular radial intervals within the insulation that separates the central conducting rod from the bushing insulator. Subject capacitive elements which are formed by the many conductive inserts would have to behave as housing between an inner high voltage conductor and the outer porcelain casing. These intermediate conductive layers are preferably arranged in radially and axially throughout the bushing configuration. Thickness of radially placed conductive layers has met to regulate the voltage field as produced around the central conductor, and that has also to ensure the distribution of voltage much more evenly throughout the bushing insulation, that is, to have a better utilization of the bushing insulation material. The length of the graded capacitor foils are to be designed as corresponds to counter the axial stress developed within the bushing insulating material so as to provide higher flashover voltage values for a given arcing distance. Now discussed with constructional features of capacitance graded type bushings. In early phase of bushing construction was mainly confined within the ungraded type of configuration whose distribution of electric field was highly non-uniform in terms of both axial as well as radial components. Electric field that would have the tendency to concentrate around the bushing flange and thus intended to create localized high concentration of stress. Bushing flange means bushing mounting flange. Especially a higher voltage, such a situation, especially at higher voltages, such a situation may force to trigger the onset of partial discharges, as because the voltage field that would have a strong capacitive coupling to the bushing's internal conductor and had to proceed along the insulating bushing's surface. Subsequent propagation ultimately forced to lead for tracking along the bushing and even resulted in flashover. Designed with a higher bushing housing diameter having with greater thickness would have been the only available solution to regulate the voltage level for the ignition and propagation phenomena at that phase. Now, See the concept of bushings at high electric field. Number one, to protect insulation of a light conductor by suitable influencing of the dielectric phenomena. To ensure, number two, to ensure the most objective purpose of controlling the distribution of the electric field strength, both axially and radially, at the inside and outside of the bushings. And number three, in spite of different types of external fault as well as environmental hazards, the dielectric strength of bushing material must have to be ensured for the total lifetime of the equipment where to be installed. After having a long technical review with these sorts of problems, certain changes are introduced mostly in bushing manufacturing practices and processes, which may ultimately lead to develop an acceptable structure of capacitance graded type bushings. For higher system voltages, capacitance graded type bushings are thus to be precisely designed for systematic distribution of natural voltage field between the centrally placed high voltage conductor, that is the inner hub, and the earth bushing flange, that is in the external hub. Manufacturing process are relatively complex as because condenser bushing is made to form from an inner voltage graded insulated core, which is rather placed between the centrally placed current carrying conductor and external insulator. However, basic constructional feature of condenser bushings is virtually be the same for the voltage rating above 25 kV to 1500 kV system voltage. As the present context, mainly three types of condenser bushings are used in high voltage or extra high voltage power transformer applications. One, resin bonded paper bushings, that is RBP bushings. Number two, oil impregnated paper, which is mostly used, YP bushings, OIP bushings, and the latest version, resin impregnated paper bushings, that is RIP bushings. Now, basic concept of condenser bushing. You see the HV conductors in the centrally placed HV conductor. Outside is the porcelain insulators. The conducting foils that has to be inserted at fixed radial intervals for distributing and stabilizing the electric field across the bushing insulation. Series connected capacitive elements that link bushings HV conductor to ground. Resin bonded paper bushing, RBP bushings. Technology of resin bonded paper bushings are mainly based on dry insulation concept. At the early stage, kraft paper was used as insulating material. Because of its hygroscopic nature, the designers had to opt for phenolic or epoxy resin coated plain kraft paper. It has already been exhibited that systematic distribution of electric field along the bushing surface is the most effective way to provide better voltage stress withstanding capability of the bushing itself. Mainly for higher voltages, the capacitive control for AC applications and resistive control for DC applications both can be achieved by inserting metallic screens into the solid insulation of the bushings. Applying all the concept, resin bonded paper bushings were made to start manufacturing in the year 1940 onwards. Centrally placed bushing conductor was first to wrap up by the resin coated plain kraft paper in an ambient atmosphere and then had to apply heat for proper bonding of the resin with the kraft paper. Sheets of electrically conductive material were made to insert at varying length between layers of wound resin bonded paper band to form field grading layers that could have been act as condenser core. The composite unit was then to be dipped in varnish and necessary heat curing process was carried out. The upper half of dry paper condenser body having with centrally placed current carrying conductor was inserted in a hollow porcelain insulator, and the lower half, that is the portion which was put under the transformer tank cover, did not have a porcelain insulator. That is, upper half is of hollow porcelain insulator, but the lower half, there is no porcelain insulator in case of RBP. Therefore, only the upper air side of the bushing did have a porcelain insulator. Due to absence of porcelain insulator at the lower half, after certain service interval, this portion would have become much more sensitive to moisture ingress, and it has become vulnerable. In the paper insulation, though it had been resin impregnated, but still might not be totally free from voids, and there would have been a chance of trapped moisture, as because kraft paper is a cellulose material. Such possibilities may have lead to enhance the partial discharge levels during service operation, and that would force to suppress the extent of operating maximum voltage level for this bushing type. However, resin bonded paper bushings were made to design for surface operations with maximum radial stress in the order of approximately 20 kV per centimeter. From the constructional point of view, it has been exhibited that the resin bonded paper condenser body has always to contain some air voids between the fibers of the paper and at the edges of the grading layers, which obviously made the bushing a poorer partial discharge characteristics. During the service life of RBP, there may be a chance of delaminating some portion of the varnished layers of the dry paper within the condenser core. Affected section of the dry paper may subsequently been soaked with oil of the transformer, and in consequence capacitance grading of the affected zone would therefore be deviated from the designed value. Such occurrence would invariably lead to uneven redistribution of electrical stresses, causing a real concern of the surrounding insulator of the bushings. Due to these limitations, RBP type of bushings is considered to be obsolete since 1985 onwards. Based on the criticality of the bushing constructional features as per voltage class, following recommendations are made by the designers. A voltage class of 26 kV and below. Bushing insulation systems can be designed to construct by using solid type of materials such as porcelain, silicone, or resin composite. B. Voltage class greater than 26 kV. Bushing insulation systems can be designed to construct by using layers of conductive materials or foils, interleaved or interweaved at varying lengths with layers of oil impregnated paper or resin impregnated paper to redistribute voltage stresses and to minimize large voltage gradients. Bushing's dielectric strength would have been further enhanced, while the capacitance graded insulated core has made to saturate with the application of mineral oil or curable epoxy resin. Now, the most acceptable one, that is oil impregnated paper bushings, OIP bushings. At operational perspective, bushings of high voltage oil filled transformer would have become the most critical component, as because the voltage gradient which developed between the ground flange and the bushing's centrally placed HV conductor is of much larger value than that of the voltage gradients developed inside the transformer or external lines coming into the transformer. From the basic concept of condenser bushings, where the coaxial layers of electrical grade kraft paper having with conducting foil interweaved at varying lengths would have to form concentric series connected capacitive elements that link bushings HV conductor to the fixing flange, which is at the earth potential or ground potential. See the figure 115. The condenser type of bushings, which include oil impregnated paper bushings, are the most widely used types of bushings for higher voltage class, that is more than 26 kV, as they have exhibited their superiority in terms of dielectric strength over the resin bonded paper bushings. Conforming with the standards IEC 60137 for above 1000 volt AC in OIP bushing technology. Constructional features of the condenser core are more or less as same as the technology applied in RBP bushings. Condenser core is rather to be constructed by inserting layers of conducting foils, typically made of aluminum or copper, at the predetermined radial intervals within the coaxial layers of kraft paper or some other insulation material, which is ultimately be located in the space between the centrally placed conductor and the external porcelain insulator. Condenser core unit, once formed, is placed in a closed heat chamber to make the cellulose kraft paper totally moisture free. Maximum water content must be kept within 1%. Then the unit is put in a dust-free chamber subjected to a high degree of vacuum, that is about 0.005 millimeter of mercury, where it has been impregnated with degassed transformer grade mineral oil. The condenser core soaked with transformer grade mineral oil is then being encapsulated under pressure in hollow cylindrical glazed porcelain bushings having appropriate creepage distance through the rain shades and other necessary fittings and accessories. In order to cope with high electric field stresses and have to maintain equipotential voltage gradient from centrally placed HB conductor to bushings flange placed at arc potential, manufacturing process must have to be totally guided by the computer aided design, that is CAD, so as to make the condenser core very precise in distributing and stabilizing the electric field across the bushing insulation. Normally, porcelain is the material used as the outer shell insulator for OIP bushings, both in upper air side and lower oil side. However, external shell of OIP bushings can also be designed by using porcelain in upper hub and epoxy or fiber wound shells with polymers in lower hub insulators, which is inside the tank, transformer tank, which is placed inside the transformer tank nearer to oil. See the figure. Oil impregnated paper bushing conforming IEC 60137 standards for 1000 volt AC. Once up to the impregnation stage of condenser core is conducted correctly and precisely, then condenser core materials must have no gaseous inclusions, and that should ensure a desired high dielectric breakdown strength, as well as the material would have to retain much higher stress levels. So far the internal partial discharge is concerned. The condenser core is thereby encapsulated in a high quality electrical grade hollow cylindrical porcelain insulator as per IEC 60815. just to allow for oil volume fluctuations as of varying temperature. A spring-loaded oil expansion chamber equipped with suitably placed prismatic oil level gauge is also installed at its top, figure 116. Spring as provided in the oil expansion chamber is mainly required for maintaining a constant pressure on the gasket in order to prevent from oil leaks and moisture ingress. Oil expansion chamber is configured with material of non-magnetic corrosion resistant aluminum alloy. Mounting fledge is also made of non-magnetic corrosion resistant aluminum alloy, which is to be duly pressure tested and would have the provision of test tap or voltage tap, air release point and earthing arrangement. If needed, may also have additional space for the installation of a ring type current transformer. In accordance with the mounting inclination of the bushing that to be installed on the transformer, suitable mounting flange would have to be designed. Test tap or voltage tap are meant for condition monitoring purpose for the condenser core layer insulation of the OIP bushings. The lower connecting end of the bushing is made to have an epoxy resin coated aluminum shield which helps to control the excessive potential stresses inside the oil filled enclosure. Some manufacturers have suggested that OIP bushings with porcelain insulators need to be stored at their preferred angle of inclination so as to have proper oil coverage over the condenser body at all times. At the present context, OIP bushings are the most widely used types of bushings for voltage class greater than 26 kV. But in several cases, for OIP bushings, it has been exhibited that over time, there may have a chance of moisture ingress, leaking of oil, gas bubble evolution causing partial discharge issues and gashing internally catch on fire during an event and corrosive sulfur issues. Ingress of moisture is the most common way to start with breakdown the oil and paper insulation system of the OIP bushings. Ingress of moisture is the most common way to start with breakdown the oil and paper insulation system of the OIP bushings. Prolonged ingress of moisture in bushings ultimately may have to damage the certain portion of the conductive layers. Most important. As a consequence, the conceptual principle of a uniform potential grading of the electric field that has been rather disturbed, for which across each of the concentric capacitors which are to be generated by the remaining healthy conductive layers would have to withstand a larger amount of voltage stress, and at the same point there will be a catastrophic failure of the bushing. Again I repeat, for which across each of the concentric capacitors which are to be generated by the remaining healthy conductive layers would have to withstand a larger amount of voltage stress, and at some point there will be a catastrophic failure of the bushings. Traditionally built OIP bushings designed with tapping, gasketing, and bolting throughout the bushing has been totally replaced by introducing hermetically sealed spring assembly. This new generation of engineering has helped to eradicate the chance of oil leakage or moisture ingression problem. However, as the moisture ingress is the leading cause of bushing failures, so it is recommended to carry out power factor testing in offline condition for tracking and trending of bushing health. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscription would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want to know, then let me inform in the comment section. Thank you. Thank you for patient hearing.